All right, this is the final part for the motor assignment. This is part two. The motor in question that we're going to be using is a 9-lead motor. It has an internal Y connection. It is going to be fed from a 240-volt system, and it does incorporate a non-time delay fuse. It is a Class A motor. It's a totally enclosed, fan-cooled motor with no marked service factor. We're going to need to know these things for a little bit later on as we're going to go through our calculations, our sizing, looking at tables, that sort of thing. Throughout this presentation, we're going to cover a few areas for the motor. We're going to demonstrate how to calculate each of the values that are required. I'll go through those calculations, how to do them, what tables to look at, what rules to reference and follow. And then we're going to draw in the correct motor connections, and we're going to explain how and why we're connecting them for the voltage source that we were given. And then as well as we're going to look at how to reverse the motor if everything's hooked up properly, but say it's supposed to go counterclockwise, but something's going on and you've got it going counterclockwise. We're going to look at how to reverse the rotation essentially. So here we are, we're looking at the system as a whole, start to finish from the disconnect. We're not looking at incoming power that was already given to us, but we're going to look at from our disconnect down to the motor itself. And we're going to look at, we'll start with the motor and then we'll work our way backwards just because the motor, it being the load, that's what's going to actually be drawing the amps, and then we'll size everything in reverse order basically from the motor back up to the disconnect. And we're going to look at our wire size needed, the insulation ratings that are required, which overload settings to use. We do have a fully automatic or a fully electronic overload that we can adjust to get a nice fine tuning. And then an overcurrent size and our disconnect size. So with the given information, that's a 3 horsepower rating for the motor. We're going to reference table 44, which is for our 3-phase motors. Looking down the 230 volt column and the 3 horsepower row, we're going to see it does have a 9.6 full load amps. In order to size the conductors, we do need to reference rule 28106. But due to rule 8104, we do need to assume the motor is going to be continuous duty since there are no specs for the motor that we were given saying otherwise. So if it doesn't say, intermittent duty or anything like that, we have to assume it's going to be on continuously. 28106 says that the conductors need to be sized for 125% of the FLA. It's at 9.6 from table 44. So we're going to multiply that 9.6 amps by 125%. That's going to give us a grand total 12 amps. Awesome. Now that we have our minimum conductor amps at our full load, we're going to need to determine the insulation rating for them. We're going to look at 28104 subrule 2. It does specify that we have a Class A motor. We are permitted to use a 90-degree rating and the 90-degree ampacity from that, and we don't need to consult table 37. However, we do need to be mindful of appendix ruling for that 28104 that stipulates rule 4006 still applies to all terminations at control and supply equipment unless otherwise specified in other areas of the code. So what that means is, yes, we have a Class A motor. Yes, we can use that 90-degree rating and 90-degree ampacity for that rating from the table we'll look at in a little bit on the motor side of the conductor. But because that same conductor is terminating on unknown supply equipment, control equipment, we can't just go with that 90 degrees. We have to go down to a lower insulation rating because we don't know what we have. If our equipment that we had was rated and we knew that for that 90 degrees, we could go with that 90-degree rating. But since we don't know, we can't. So we're going to look at 28104 stipulates we're going to use a 75-degree rating. So we're going to follow that. And then that's going to say basically we have to look at table 37, and it specifies we can follow table 37 without having to look at that 90-degree rating. So looking at table 37 here, we were given the information the motor is a totally enclosed fan-cooled, which we call a TEFC, Class A motor. We're going to take that to 37, and we're going to look at the type of class we have, which is Class A. We're going to line it up with the cooling. We're going to match it. Pretty self-explanatory. Looking down the Class A column, and since we do not have a totally enclosed non-ventilated, we're going to look at the other row, which encompasses everything but. And here we can see we have that 75-degree insulation rating, which is required. Based on that, we can proceed. We're going to select our wire size from what we know. Alright, so based on what we found using the 75-degree insulation class from table 37, we're going to look at table 2, since it mentioned we're using a copper conductor in our power cabling, no aluminum, following the 75-degree column from the insulation class that we found earlier. And now we're just going to be looking for the 12 amps that we had calculated previously from our conductor cabling. And we're going to find that number 14 is large enough for what we need. Our next step is to calculate the overload setting. Alright, so we're going to look at rule 28306 to do so. Since our motor does not have a marked service factor, we're going to take a look at sub-rule B, which states 115% of the full load amps will be used to select the overload device. So basically what that boils down to is we're going to take our 9.6 full load amps, we're going to multiply it by that 1.15, and that gets us a grand total of 11.04 amps for our overload setting. Since we do have a fully adjustable electronic overload, we can set it to quite a specific number. We don't have to go down to the next lowest. Alright, so now that we've got our motor full load amps, our conductor size, our insulation rating, and our overload setting, we still have to select the disconnect size and the overcurrent device. Looking at rule 28200, we can see that we cannot exceed the limit. It's calculated in table 29. We were given the parameter of a non-time delay fuse, so we're going to use that column. Because the wound rotor motors are a specialized unit, which have additional rules to them, we're going to default to the squirrel cage induction motor row, which gives us a total of a 300% rating of our full load amps. So we're going to take our 9.6 full load amps, we're going to multiply it by 3 to give us a grand total of a 28.8 maximum overcurrent size. Excuse me. Looking at table 13, we can see that since 28.8 amps is the maximum, we will have to step down a little bit. So we're going to drop down to the next highest there is going to be our 25 amp fuse. With a conjunction with that, we're going to use a 30 amp disconnect size since it's the smallest that'll fit with that 25 amp fuse. And that should be everything covered there. Let's do a quick little review there. Starting at the motor, we've got a number 14 wire size, a 75-degree insulation rating, a 11.04 amp overload size, a 25 amp overcurrent size, with a 30 amp disconnect. That's going to cover all the calculations for wire sizing and all of that. And now we're going to move on to the actual how to actually wire this motor and the connections and that sort of thing. Alright, so our motor is a 9-lead Y-connected motor. It means there are some internal permanent connections that cannot be redone. In addition, this wire can be wired rather for a 230 volt or a 460 volt, but since this application is for a 230 volt system, we're going to wire the motor in a parallel connection. Here we can see the individual windings of the motor. Those are the little windings there in black, forming that Y pattern. Note that there is that star point in the middle. It is a fused link. It's a permanent connection that we cannot alter it. We don't even have access to it. In order to wire for the required 230 volts, the motor will need to be wired in parallel, which are those red connections that are made there. Should the motor be connected to a 460 supply, we'd connect it in series, but parallel will work with what we're doing since we are working with that 230 volt application. Alright, so here we can see that, bam, terminal 3 is going to connect to terminal 6, terminal 2 is connecting to terminal 8, and terminal 1 is connecting to terminal 7. Right in the middle there is your star point. Would be where terminals 10, 11, and 12 would be. However, they've been permanently fused together there to make that star point. Last, we can see that T5, 6, 4, 5, and 6 are all connected together as well. All right, that's that one right there, making that a little semicircle. In some cases, there will be a T0, which is just a connection point between the T10, 11, 12 and that T4, 5, 6. Not all motors have it though. We can also see right up at the top there, that red horizontal line would be where your A phase connects to that terminal 1, terminal 7 connection. B phase in black on the lower right is connecting to your T2, T8 connection point. And then C phase is the vertical blue line, bottom left there, is where it connects to terminal that 3-9 junction there. All right, so this is the actual motor itself, and now we just have to wire the actual connections. So using our terminal connections as a reference, let's get started. First, we're going to look at T1 goes to T7, T2 is going to go to T8, and T3 is jumping to T9. Just those same connections that we made, but now on the actual leads of the motor. Next, we can see that terminals 4, 5, and 6 are all connected together, and that's covering that semicircle of our wiring diagram there. And that's the inner connections for the actual motor is done. So now we need to actually, bring our power to our motor. So here we can see that line 1 is the red A phase, connects to terminal 1. L2 is the black B phase, connects to terminal 2. Line 3 is the blue C phase, connects to terminal 3. And again, terminal 3, terminal 9, it's a parallel connection, so it doesn't matter which one, but 3 to 3 makes more sense. Finally, all we've got left there is our little bond wire down to the bond screw for the actual housing unit to bond the whole system. All right, so with that, we're fully wired up. We sized everything that we needed. This motor is good to go. It's up and run and, happy-go-lucky. But what happens if you wired it all, you've tested everything, your volts are all good, everything checks out, but when you start the motor, it's going the wrong way? Have some unhappy customers. If you've already connected your loads, hopefully doing a proper commission, you're doing a full test without coupling it to any loads, right? I hope. So in order to get that reverse rotation, while you can swap any two lines, will reverse the motor direction of rotation. Best practice would be to swap your A line and your C line. In this case, we're going to have A line is going to connect to your T3 connection, and the blue C line will connect to your T1, T7. Just like that. There we are. All right, so good luck in the field, rookie. Hopefully you keep that magic smoke in and make sure you keep those motors up and running properly.